Right now we're going to go back and discuss a topic we looked at quite some time ago, which is solubility. Previously, we looked at solubility in a very qualitative fashion. Things are soluble or they're insoluble. Later, we went back and did a little more detail. Okay, even soluble things have a limit. You have an unsaturated solution, means you could still dissolve some more solid. Saturated means you've dissolved as much as you can, and supersaturated means you've somehow shoved in more than you can. So we took a closer look at solubility, but it was still very much a qualitative description. So what we're going to do now is go back and look at this in a quantitative fashion. We know solubility is a spectrum, so there are varying degrees of it. When something is soluble, it does have a limit for how much can dissolve. And even if something is insoluble, we can expect that at least a very small amount of it is going to end up dissolved in solution, just not very much. Sometimes we're very interested in that, though. If you have a poisonous substance like lead, even if it's only very, very, very slightly soluble, you want to know exactly how much is being dissolved. So in order to quantify solubility, we use what's called the solubility product constant, or Ksp. So let's look at calcium fluoride as an example. If I take calcium fluoride as a solid and dissolve it in water to make aqueous calcium and fluoride ions, I can write an expression for that Ksp. And if we notice, all it is an equilibrium constant. It's just the calcium times the fluoride squared. Of course, the solid gets left out because solids don't get included in equilibrium constants. So the Ksp is just the equilibrium constant that describes this dissolution reaction as the calcium fluoride dissolves, also sometimes called a dissociation reaction. And we can sometimes also describe this in terms of molar solubility. Knowing the Ksp isn't really that helpful other than knowing if a lot dissolves or a little dissolves. The molar solubility actually tells you how much of the solid will dissolve in units of molarity. So Ksp is nice because it gives you an idea, but the molar solubility is a more tangible number we can use to figure out exactly how much is dissolving in solution. And they're very, very closely related. So keep in mind that solubility product constant is a constant. It's an equilibrium constant. It does change with temperature. Solids become more soluble with increasing temperature, so we would expect their Ksp to increase. But at a given temperature, it will stay stable. So typically in these types of problems, we're either asked to figure out what the Ksp is or what the molar solubility is. So we approach those nearly identically. Let's look at what that problem might look like. For example, determine the molar solubility of calcium fluoride, for which Ksp is equal to 1.46 times 10 to the negative 10. You always start these problems the same way. First, you write the reaction for calcium fluoride dissociating. So we're going to start with our solid calcium fluoride, and it's going to dissociate into two pieces. So if we go look at it here, we need to think about where we're going to split it. And this one's easy. We're going to split it between the calcium and the fluoride. So when that breaks apart, it's going to produce one calcium piece, and it's going to have a charge of +2. We can get that from the periodic table. And it's going to produce two fluoride pieces, and he'll have a charge of -1. So we have calcium, which is +2, fluoride, which is -1, and now we have our dissociation reaction. So after we write the reaction, the next thing we want to always do is write the expression for a Ksp. So this is just the equilibrium constant, so we're going to do products over reactants. So I'll have calcium, and then my fluoride, but because there are two of the fluorides, I'm going to put my 2 up there. So I'm going to write my reaction, I'm going to write my Ksp expression. Now I need to figure out which piece I'm solving for. I have Ksp, so I have the number that I can plug in here. I want the molar solubility. When I want the molar solubility, what I'm basically going to do is create an ice table and solve for X. So let's go ahead and create our ice table. We're always going to leave out the solid, so I really just make my ice table just under the second half here. I always assume that I started with 0 of these pieces. I started with just the solid. I produced a little bit of each as it dissociated. Because there's a 2 here, we need to make sure we do plus 2x. So keep our stoichiometry in mind. So I'll make x of the calcium and 2x of the fluoride ions. Now we have our Ksp and we have expressions for calcium fluoride, so we can plug those in. 1.46 times 10 to the negative 10 is equal to x times 2x squared. So let's go ahead and simplify the right side here. 1.46 times 10 to the negative 10. Oops, that's a 10. That squared goes to the x and the 2. So 2 squared gives me 4. And then I have x times x squared gives me x to the cubed. And now I'm just going to solve for x. So first I'll divide both sides by 4. And then I will take the cube root of both sides to get rid of that. So I'll do that and determine x. And I find that x is equal to 3.32 times 10 to the negative 4. And because that's the amount that dissolved, we give him units of molarity. Now, it's not obvious at first that this is the molar solubility, but if we go back and look, if we think about it, the molar solubility is the amount of the solid that dissolves. Well, there is a 1-to-1 ratio between the amount of solid that dissolved and this x we have here. So if 1 mole of calcium fluoride had dissolved, then we would have 1 mole being our x, because that's how much calcium fluoride we would have lost and how much calcium we would have gained. So by working backwards, we can see that whatever x is really tells me, even though we don't include it in the ice table, that's basically my minus x over here. I had to lose that much of my solid to make that much of my ions. So when you solve for x in this ice table, that's really telling you your molar solubility. So if you're given Ksp and asked for molar solubility, make an ice table, solve for x. Really simple. Of course, we could be asked to do it the other way. So here we have PdSEN2, and it tells you it has a molar solubility right here, and it wants Ksp. Good news is we start almost the same way. First thing, we need to write an equation for how this guy breaks apart. We can see that the SCN is in parentheses. That must be a polyatomic, so I'm going to split it right there. So I'm going to have my PdSEN2, which is a solid. It's going to dissociate. So I'll get a Pd here, which is a charge of +2. And then I have that 2 there, so once again, now I'm going to have 2 SEN has a charge of -1. So I need to write my expression for Ksp. So that's going to be my Pd times my SEN. And this has a 2 here, so that guy is going to be squared. Now I'm going to make my ice table. Don't worry about this guy. So I'll make my ice table and just worry about my aqueous things. I start with 0 of each of them. I make x of the Pd, but because of this 2, I make 2x of that guy. So I end up with x and 2x. And now I'm going to think about what pieces I have and what pieces I don't. So I want to find Ksp in this case. I want to find this guy. What I'm given is the molar solubility, and we saw from our last problem that the molar solubility is essentially equal to x. So what I can do is say, oh, I have x, right? X here is equal to 2.22 times 10 to the negative 8. And here it's going to be twice that much, 2 times 2.22 times 10 to the negative 8. So now that I have actual numbers for my equilibrium row, I can just plug them into my expression for Ksp. So Ksp is equal to my palladium, which is 2.22 times 10 to the negative 8. That's a 10. And then my SCN is twice that, so 4.44 times 10 to the negative 8 if I do this math here. And I can't forget to square that guy. And so I get this very tiny number, 4.38 times 10 to the negative 23. So I have a very, very small Ksp here. We can see I started this problem the exact same way. The only difference is when you're given a Ksp, you're trying to solve for x, so you plug it in, rearrange to solve for x, and that's your molar solubility. If you're given molar solubility, they're telling you your x, so you can plug that in at the end of your ice table and then go ahead, put it into your Ksp expression, and you should be able to solve for that guy really easily.